Hello, good afternoon. We'll get started in just a few minutes. Welcome to the stream if you're already here. It's been a couple weeks. Just to recap what we did last time, we were working on the entry format for Berkeley DB in Rust, and we were looking at the how to implement an algorithm that would walk through all of the entries in the database. So that's going through all of the pages that are leaf pages, and iterating over their keys and values. So the there were some interesting things with having the database be the source. So like a DB struct be the source of information that we would read from. And all of the other things, all the other abstractions we built last time, just borrow from that database struct. So, things like the abstraction around a page or around an entry in a page, those were all temporary. They had lifetimes in their type signatures. So this way, we wouldn't induce a bunch of copying just to read. Now, we did do some copying. Some of that's unavoidable, just with how we needed to convert some of the contents of the database into numbers that are useful for computation, or bookkeeping about the database. So we've got a lot of that done. Where we left last time was in the middle of implementing our tree walking algorithm. I was running into some compiler issues, and it was my old friend, maybe not friend, overlapping borrows, and I didn't see how to resolve it right away when we were ending the stream, and it had already been 3 hours. That was one of my longest streams ever. So it's funny. Pretty much right after that stream ended, I figured out what the problem was and how to solve it. And it's actually quite simple. So today we'll start with talking through what the solution to that is, and sort of why Rust forces us to do that. And I think it's a good lesson in that, while there was nothing per se in that algorithm that would have caused a memory safety problem, Rust is errs on the side of being more conservative. So it errs on the side of being sound over complete. This is a fundamental trade-off in any type system and compiler. So in this case, there were not an issue. There was not an issue with mutating the things that we were mutating, while we were also borrowing parts of that structure immutably. But the Rust compiler forces us to make sure it's safe. So like, there's no way that it could violate having both mutable and immutable aliases, or references is the way to put it, available at the same time for the same object. Okay, so now that I've done that, welcome. Nice to see a bunch of you back. Let's look at the code and what changed. So I'm going to switch over here. So this is our main. We're going to change this to fit the walking algorithm. This was a very naive one, which is just iterate over all the pages and then iterate over all the entries in the page, and print them out. We were working on last time a more sophisticated algorithm that walks the tree. Um, so let's look at that algorithm. So if we look at database, and I think it's worth showing the difference between what we committed last time and what I've changed, so we can understand why. Um, and we'll just do a get diff here to show. Okay, so ignore that stuff at the top first. So last time we had, um, well, I guess there's a bit more here. We kind of left it in uncommitted state. Um, all right, that's probably not that useful. So what we were doing before is we didn't have these variables here, and I'll talk about why those are necessary. Um, but what we were doing is, so in here we were saying self.entry is 0, and then self.pageNo is next in this step of the iterator. But that's not allowed because we're at the same time borrowing a page, and we're borrowing it immutably. So now we may be able to remove this clone. We'll find out. But the problem is that this page is still active until the end of this scope down here. But in here, we're going back and we're trying to mutate the same structure from which this is borrowed. And that's not allowed by the compiler. And so what that is called is overlapping borrows. So the solution was to copy, since page and entry are just integers, usize, we can copy them out into local variables, which we can mutate freely because those don't overlap with the borrows in here. They are a separate allocation. Now it just so happens that there's these are probably in registers, and this is a very cheap operation to copy this usize into a local variable on the stack. Okay. So then we modify the local variables of page number and entry in this iterator until we know that we have reached either the end, like the next entry, or we've reached the end and there's nothing more we can do. So then after we've determined this is the current place, we either found a pair of entries or have to stop and return none. Then we set the page and the entry on self based on those local variables, and then return the results. So in this case, the mutability is only for this span. Everything above here, we're using self immutably. I'm sorry, this is one that's also mutable, but that span ends right there. All of this inside the loop is immutable, and then we return the result. Now I do want to see if we can avoid this clone. Now the clone is cheap, but if we can avoid it, yeah. Let's see about that. Okay, it's still compiling, so we're fine on that. That's good. We can avoid an additional allocation in this loop. Yeah, so that solved our mutable and immutable at the same time problem. And so now we should be able to test this structure, this walk structure. Now it's complaining that none of these are used because we never call this function. So let's do that. Let's update our main. Oh yeah, and there's a couple of the minor things that I updated here. We have this generic lifetime in here, which is the lifetime of the reference to the database that we're borrowing from. And so these are all, tagged with that tick A. I could probably make it be like tick DB, and then it'd be a little bit more descriptive. Maybe we'll go back and do that later. But an interesting thing here is that we had previously, and this is visible in the diff. We had tick A self, and these entries had tick A in that generic argument as well. And it at that point, it complained to me that tick A was not generic anywhere. So I put in the generic, like the turbofish, well, not exactly turbofish, just the angle brackets, like so. And then it's like, hey, that lifetime's not necessary. So so just remove the lifetimes, and then the compiler is inferring that this generic lifetime, it could be anything, honestly, but it's probably based on self there. So we don't need to worry about providing a ton of information to the compiler there when there's only one lifetime generic. So in this tail position, it's able to infer the lifetime. Okay. Yeah, and note here that partly happens because we have this tick ADB right here, and that becomes the generic inside this structure. So we know that all of these page structures that are in this vec have a lifetime that is bound to this, and since that lifetime is the same lifetime as the entries extracted, then it all works out, and it's like, yeah, I know what that lifetime is. Okay. Yeah, so we did basically this. I wonder if we can do current page. Okay, so now that's a little bit cleaner. I like that better because it has semantic value naming that thing. Okay, so now that we have that, let's go back to main. I want to see what the changes were in page before we move on. I don't recall if there's any. Okay, so we just derived clone, and then it looks like there's, yeah, because this is there, we don't need to assert that this borrow has the same lifetime as that. In fact, it may have a shorter lifetime. That may be the issue. Yeah, okay. We just derived clone. Now that we're not using that, it's not so important because we're not cloning the page. But it doesn't have any harm. Honestly, page is this header struct, which, while not small, is not the largest thing in the world, and then a reference to a slice. So I think we're okay to leave that. Okay, so let's go back to main, and we're going to just comment all of this out. Previously we did looped over all the pages. Actually, let's leave debug printing the page headers, because that kind of fits. If you aren't following, we're working on this page, and if OBS and Twitch will allow me, I'll paste. Okay, it just doesn't allow the key combo. This is the page we're looking at. So we're looking at the task here, and it's basically like this. They express it kind of semi-recursively. We're doing it with Rust iterators instead. And our example output is like print the page information. This one, they print out the raw data. I'm not going to do that, at least not yet. I think it's more important to get to other things. This is like, hey, implement a hex dump, which I'm not particularly interested in implementing right now. Um, it's fine, it's whatever, but we'll probably have to do some because we'll want to print potentially the keys and values. Um, yeah, so we might need to do something like this. But let's just go in here and do like print line key value data like they do. And then we're going to for key value in db.walk. So here's that iterator we just created. And we're going to do print line, 4 spaces, key. And we need to look at what's in the entry. Yeah, it's just, it's just got a slice, a length and a slice. And we didn't implement, no, we derived debug. So let's just for now print it with debug, and let's not add new lines. Value, and do the same. So if our algorithm is correct, we should get an output that looks sort of like this, except we're going to have bytes and length there. And we may want to perhaps implement display for entries. That might be interesting. Let's get this first and see what we've got. Helps if I'm in. Okay, we're ignoring the things that it says are dead code. Oh, I need to pass it. Test data.bdb. Okay, so yeah, it's interestingly, it's not making progress. So we have a flaw in our algorithm. See what like 98 is. That's B, so that's the very first entry. If you missed previous sessions, why did I just pull up the Erlang shell to do that? Because Erlang treats lists of numbers as strings when they're all printable. So it's an easy way to check what happens when I give you a list of integers. Okay, so it's stuck. It's stuck on the first entry. So clearly our algorithm has a problem. Okay. So we're zipping together the 2 entries. So it should come key value, right? So if the entry is longer, or the entry number is bigger, but we're not hitting that. We're not advancing entry. So if the result is none, it means we didn't find anything. But we're finding the same thing over and over and over. Why don't I do we'll just take 5 so we don't iterate forever. Because I want to see what happens when we reach this spot. Let's do print line entry page no entry and maybe we'll figure out why it's not incrementing. Because if we got a result here, we should bump this by 2. The interesting thing here is yeah, if we got none and there is no page number, then we should break. There is no next page. But we'll do that here anyway as we fall through. Let's print and see what happens. Okay. Page 2, entry 2, page 2, entry 2. So it's not increasing. Why is it not increasing? Oh, we aren't. This is not correct because we need to get the local variable page. Not that that's going to change. Like there should be more entries in this page. But yeah, let's do. Let's do this. That'll ensure that if. Oh, that's why I had that page number. Let's say current page. And this is current page. Yeah, it's the problem of having things that are similarly named. Okay, so we should never be reaching this branch. But it's almost as if these aren't being set. Let's run it one more time. I wonder if it's yeah, it's got to be this move to leaf. Let's look at that. Okay, yeah, here's the problem. If we're already on a leaf, it's setting it back to 0. I think the problem here is if we're already on a leaf, I think I'm gonna move this. If we're already on a leaf, we should just break out. But if we are in a B tree or the metadata page, we should set the entry to 0 so that we're always starting at the first entry of the first leaf page. If we're already on a leaf page, we shouldn't change it. Yeah. All right, let's try that. I feel a little bit icky about this still. um but let's try it. Okay, now we're advancing. Okay. Yeah, so that was the source of the problem. So this is at the end of this one call into the iterator. We're at entry 2, and then we're at entry 4 and 6 and 8 and 10 and so forth. So that should be correct now. And let's remove that print from that. And we will run again. Okay, so we're still only taking 5 pairs. Let's remove the take from this. And there, we went through every single page pretty dang quickly. That's nice. I think we can now maybe consider implementing display for entry, and then we can get it printing out as strings, so to speak. What I want to do is look at the ways we can convert. Yeah, so we could do from UTF-8. Well, it converts a vector bytes. Maybe we want... We don't want to make a new allocation to print it. Maybe look at stir. Maybe there's a way. Okay, so there's from UTF-8. This returns a result. Yeah, okay. So if it's not UTF-8, one thing we could do, because they're in their example, they've got this hex printing stuff, and then they've got the string representation on the right. One thing we could do is perhaps iterate through the bytes themselves, and for each byte go, is this ASCII printable? And I want to say that's there's a method on U8. But yeah, something like, there's all these is ASCII. Let's escape ASCII. Hi Isaac, welcome to the stream. Welcome back. Yeah, we don't really need to test. We could say is ASCII, right? This just says, is it in the byte range from 0 to 127? That's nightly. Okay. Um, yeah, let's just try that standard stir from UTF-8, and let's do that. So let's impl. I'm gonna use standard format display. We're gonna use standard stir from UTF-8. Okay. So let's impl tick display for entry tick A. Okay. And so what we want to do is match on key data. So we could do if let and we can ignore length because we don't care. We know that the way we constructed it, the length is the same length as the slice. Self. We'll just write. That's not good, but so let's do. It's not f dot right. It's right bang f, right? Okay. And here we'll do right f, and we're going to do I'm going to remove this else. And we're going to do if let OK s is from UTF-8 data, and that way we'll do return right f s. Otherwise we'll fall through, and we know that it's not UTF-8 data, so we'll just print ... And that will apply for internal nodes too. We can maybe put a to do in here, which is implement display for internal and overflow nodes. We're not handling overflow nodes yet. Entries, excuse me. Variance. That needs to be right bang because that's a macro. That's a stir. Oh, that needs to be a format string? Yeah. Okay. So now what we'll do over here is, instead of using that, we have display implemented for entry, so we can just use display. And hopefully we'll get something a little bit less less messy than this. Our data is garbage, right? It's just test data. But being able to print it out for our testing sake is going to be nice. Okay, so we get something much more similar to what they got in their output down here now, right? Cool. That wasn't so bad. All right, we're going to undo this. Okay. I would say, with the exception of not really implementing overflow entries, the description here is not great. Like, it's like, okay, you've got all these fields, and how do you know when it's an overflow entry versus an internal entry? Yeah. Is it because it's always 12 bytes? Is that how you know? Seems sketch. Okay. I think this is a good place to make a commit. So let's go ahead and do that. And lately, I don't know if you all have done this, but like I've been missing the maggot porcelain for which was Emacs only. Super good porcelain for Git. But a friend clued me into Lazy Git, which is almost as good, and I've been really enjoying it. Um, so we're going to go ahead and use it to review our changes and make the commit. So I'm using page up and page down to scroll the right pane there. You can do partial adds. I'm not going to in this case, but it is possible. So, which is really nice. Okay. And then our main, and what we changed page. Okay. So this is session 3. We are finishing the walk algorithm and implement display on entry. I think it's a pretty good description. Okay. All right, so let's start looking at the next bit. I want to scan through this. I may have mentioned in a previous session, our goal is not to make ABI compatible with Berkeley DB. That might be interesting in Rust, and to look at all the things you would need to do to make a library that is accessible from C and from other programs that can import C libraries. I'm not actually that interested in doing that. I think that might be an exercise in frustration. And it's kind of weird. I think that the author wrote their implementation in OCaml, but they don't reveal that until later down in the series. Yeah, maybe it's in here, but the main thing is that there's this, db.h, which is defining the implementation of this Berkeley DB interface. It's kind of a strange, I won't say strange dialect of C, it's a strange style in that it has associated functions, even though this is just a struct, which we could potentially look at this db.h, find that, and inspect it and see what we could do to emulate that interface. But let's just look at maybe what we can do instead is look at what is the interface they expose, and can we make something in Rust that looks similar but doesn't have the exact same ABI, right? If you don't know what ABI is, this application binary interface. So it's a specification, a combination of how the compiler will expose symbols that point to functions and types in the compiled binary, as well as what are the signatures of those functions, especially. Okay, so in this, it looks like the author has annotated this function signature with their own commentary. So this pointer. There's a transaction ID, so you could transactionally create a database. That's a little weird. Maybe there's a transaction manager in BDB. and it ensures that that database is created. I don't know, with inside a transaction. So weird. Okay, so then it takes the path, the string name used to assign to the database. This must be like there's a registry or some kind of thing when you print some debug information, it annotates what the name of the database is. It's not stored in the data structures that are on disk at all. Um, note here, the database type must be DB btree, and that's 1. We ignore ignore the flags. And then the Unix mode, opening the file. So mode of 0 should be interpreted as user and group read and write. Yeah. Hi, Chris. Thanks for coming to my stream. I had a thought about your 16-bit versus 8-bit images yesterday, which God, that was so weird. I wonder if ImageMagick does something really stupid when trying to expand 8-bit to 16-bit. I wonder if it just shifts left the 8-bit values, and then so you get this super desaturated bright color. That would be funny. Yeah. Yeah, you totally didn't expect a scaling of 8-bit color space to 16-bit color space to wash something out, but that's what happened. Weird. Also nice that you got that file size down, 60%. That was pretty cool. Okay, so they've got this big open function. Interesting that this takes a pointer to a DB. So what I'm guessing is the sort of thing that you do would be to declare a variable DB inside your function, and you pass a pointer to that stack allocated DB. And there's no guarantee that it's not uninitialized memory, which it probably is. In C, hit another foot gun. But you would, this function, in addition to attempting to open the file, would probably fill this struct, this pointer. So this is just saying this is the space I want you to put it in. Basically an out param. Okay, so then close, in another flags thing that's ignored. Also, this pattern of returning 0 on success, non-zero on failure, we would want to use results. This is, so open and close. Stat print. Okay, print statistics about the database. Okay. Yeah, so he's saying there's a number of members of possible use and interest, but really all you need is a place to stash all the instance data for a database. And he's saying we have BT internal, so that's btree, I'm guessing is what BT stands for. So if we were to put your file handle or anything else, just make up your own struct for all the information and store it in BT internal. If you're writing in C++, this is a great place to keep this pointer. Okay. Yeah. More fun stuff. So this is create a DB instance. This involves allocation. So they've got a star pointer here. There was a great meme I saw this past week. It's like someone trying to explain what a pointer to a pointer was, to an int, in C, and it's like that, the character pointing back like this, and there's another character pointing back here. So you've got a pointer to a pointer. It's often the case where in C where you have out params, so to speak, where the this function db create essentially does an allocation of the struct and then passes the allocation as this part. So, this is a pointer to a pointer. It's like, hey, I made an allocation. You have some space on your stack, which is the first pointer. I'm going to put the pointer to the thing I allocated into that slot. We don't do this in Rust. God, it's so confusing. Yeah, so, they talk about the C implementation. Um, Note here that what they do is, like, again, they're saying here, this is a pointer to a DB, and we're just going to use calloc. I don't know why they use calloc instead of malloc. That seems so weird. You only are getting one, so why do you use calloc? Whatever. Yeah, I had to deal with reading out params for ray tracing in one weekend, which is very not that many. Yeah, like I think that there's sort of like an inversion of control problem here, and not in the sense of dependency injection, but in that, like, who's going to be responsible for allocating. And I can understand why in this sort of like library scenario that you would want to control how things are allocated potentially. Very good one, Isaac. A 2-star program. Wait until C code from a 5-star programmer. Yeah. But this is just, C. I don't know. Okay, so this is a pretty short chapter of this. I think probably what we want to do is focus on, do we have the correct static methods, so to speak? They're not static, but the type struct methods to open. They should return the right values, and then so like we should have a result of a DB as our as the signature of our open function, right? And then close should consume it, so we'll be able to use move semantics on that, which is nice. And we're not, this goop here. This is like, hey, we have an implementation. Of DB open, and we're gonna, this is a function pointer. This is not a method. So, God, the hoops you had to jump through to do C. Okay, so we're not going to do, this is the task, which is, like, let it go through all these steps, open a DB with, create semantics, or the create flag, print the stats about it, and close it. So I think let's look at what we've got. We already have a DB open. So let's go up here, and we'll eventually want to change this buffer from reading the whole database to maybe be a file handle, which we can seek around, and then a cache of pages that have been loaded, potentially like a sparse cache. Not sure yet, but the very first thing we can do is go, okay, well, this DB open, looking at their signature here, note that this is this is important, the file name is important, and potentially the mode, and we're just going to ignore any other type than btree. So why do we care? So we have it's going to be really interesting to have a mode in a platform neutral way. So let's change this first to result self, and then we have, so this can return IO result. So we can actually just say this is standard IO result of self. And then we'll just do question mark here. And that means we need to do okay self. So that, what was it complaining about? Well, we'll find out. Oh, it's complaining that we didn't, we need to do this and say this returns standard IO result. Now we probably at this point pull in anyhow, use anyhow result. But for now we'll do this, and we need to return okay. Okay, so now we've at least handled the case, or we've exposed the case that you might not be able to open that thing. Which, in that one point earlier where I just did cargo run and didn't pass a file name, it blew up. So we could also do like this unwraps. Let's do expect please pass a database file name. And if we cargo run with no arguments, we should get please pass a database file name. Yeah. If we were actually making this a program that we would be shipping to people, maybe it would be important to make that more useful. But it's basically just testing. Okay, so this is better. So let's make a close. And this is going to be real simple. Honestly, it's just going to drop. It'll do nothing. But it consumes self. So at this point, that buffer is going to get dropped. This whole struct is going to get dropped, and since we haven't implemented writing, we have no file handle to close. So that's there. We've implemented close. We could do. He says this function meant to print statistics about the database. Instead, I'd suggest taking your code from printing page and entry data and making it accessible from here. So what we can do is copy this out and go here, stat print, and borrow self, and we'll change DB with self. Okay, and then from main, we will call db.statprint, awful function name. Okay, and then we close. Again, this isn't strictly necessary because we'll drop it at the end of this scope, but we're kind of following the whole ABI there. Pointers to functions. Yeah, okay, so here's saying, yeah, or don't do that. If you're working in a language with bindings and it's easier to make a minimal abstraction layer over your own API and the existing Berkeley bindings, write tests on top of that, then do that. Yeah, I think their goal here is to ensure that you can write tests that exercise the same functionality. Yeah, or just like don't. Yeah. Now, what we could do real quick, and I'm sure it's out there. We could look for Berkeley DB. Yeah, so this is statically linked Rust bindings for Berkeley DB. So we could just use this in our test suite. Um, and let's, yeah, it's gonna be, they've kind of made a Rustish API on top. Um, oh, that's interesting. Key as mute slice. You need to pass it as mute. What? Okay. Okay, so this is linking to the actual Berkeley DB library. I think since this has, kind of what looks like a little bit of a rich-ish Rust API, um, I don't know that we could reasonably take what we're building and swap it in to have the same interface. I actually kind of dislike this interface. I understand why they're doing it, builders and all that make certain things easier, but um, mm, yeah. Okay, so there's a lot of concepts in here that are in the database that we aren't going to handle yet. I think the environment is sort of like this space in which you would create a database, and maybe that's the whole registry idea of naming it. Yeah, probably a syscrate. Yeah, let's look for that. LibDB sys. Um, and if we look at this, it's probably going to be really, yeah. This is going to be the bare the bare API. Um, oh wow, and it uses. Oof. So we look down here. Yeah, this is going to be bind generated, I'm sure. Lots of constants. Statics, oh fun. And the functions, and these are all unsafe because they're from bindgen. Oh god, it's like pulling in things from libc and oh geez. So this is the sort of, yeah, let's look at the, yeah. So they it's such as a type alias for this thing, um, and that's the actual DB struct generated from the sys, the bindgen library in this. And this is the field that he was talking about. And you just put whatever you want in it. Okay. Again, this series is not about making a production ready Berkeley DB implementation. This is about learning what the internals of this thing are. So um, I don't feel like I want to spend any more time on this. Let's look at point reads, and hopefully we can finish that in the next hour. Okay, so support for searching down the tree in search of a single value. Okay, so Berkeley DB offers a get method on DB, allowing the reading of the stored value corresponding to a key. To represent a key or value, it uses a dbt struct, which describes the memory and its size. Database thing. That's the actual comment from the source code. Oh man. Okay. So they've got the data, which is a star, void star pointer. So basically bytes, as far as we're concerned, and then the length of the key. Um, I'm not sure what ulen, dlen, and d off are. And then you can, I guess, put opaque data into this struct. Let's look at their official docs here in a second. So the get method is implemented to implement is defined as, okay, get the value for a key. Right. So is the user's responsibility to manage the memory pointed to by key, ensure that it is valid for the lifetime of the call. Yeah. So they're concerned about these these parameters. So data should be zero initialized upon calling get. Well, what we can do here is there's what we can return from here is an immutable slice in our version. We don't need to have the caller allocate something and pass it in as a mutable slice. That's or a mutable vec. That's silly. That's a horrible API in Rust. Okay, so data should be zero initialized and is yeah. Library's responsibility to manage the memory pointed to by data dash data. Okay. This memory will remain valid until the next call to the library, which returns a DBT. This feels like an implementation detail that's kind of leaking through their API. Why might that be? So this is a pointer. So they're saying pass the null pointer. Maybe there'll be examples down below. And I'm guessing the whole lifetime thing, it's saying manage the memory pointed to, DBT is this struct up here. And basically we can return an entry, right? Or we can return a slice, as I mentioned. And the lifetime would be figured out by the compiler, and we don't have to worry about that. But I suspect what they're doing is they're reusing some structures internally. So as soon as you call something that uses a DBT again, then it'll reuse that struct that it previously allocated for this. Kind of jank, honestly. Okay. We may run into some more of these issues if we eventually move toward using a file handle and, caching, potentially evicting pages rather than just reading the whole file at once. So that's something to take into consideration. Okay, but let's look at the rest of the parameters. So DB, that's self. The transaction within this getter operation is scoped. So they're saying null, so we'll have a transactionless get. Okay, so DBT owned by the user to describe the key value pair to fetch, which is just a key, right? And then data is zero initialized DBT. Oh, maybe that's different. Maybe that's you're supposed to allocate this either on a stack or heap, however you like, and then mem zero it. Okay. And it returns zero if the key is found. We can use option. Yeah, or db not found if the key was not found. Yeah, we can use option as the return type. Okay, so the default, this is where they're talking about. The default mode of operation is the library is responsible for freeing or reusing any return state when the next call to any data returning operation is made. The way that this works is the db struct has members which let you store what had been returned to a user previously, so you can remember what pointers had been returned on a previous call. Basically caching it for you. There's more to remember for other APIs, but for now we only need to remember what was returned in the data argument to get. Yikes. All right, I had opened another tab. Yeah, this isn't very bright. um, that's not helpful to me at this time. Let's close this. Okay, their flags you could optionally support to make it easier to write tests or demo code. Okay, data was allocated, so the flags can say that this was allocated with malloc. It's the caller's responsibility to free. And user mem. Okay, so these are the things up here, right? User mem. So data was allocated by the user and points to a region of memory size ulen. Okay. So to me, this feels like they've conflated memory management with key fetching. And for a library that was created in the 90s, I kind of understand that, or the early aughts. I kind of understand that. It does feel like it's really conflating concerns for the sake of efficiency. Okay. Okay, so this is where we're actually getting into the internal entries. We basically, in our walk algorithm, we were like, let's just go down the left portion of the tree and walk along the bottom, which is the most efficient way to do that sort of thing. But for a point read, what we want to do is start at the top of the tree, look at, okay, which internal nodes do I need to follow to get to the leaf node that contains this entry, or potentially contains this entry, because B trees are sorted. So let's look at what it says here. So examining the entries in internal B tree page is going to yield internal entries that look like, so we've got offsets, and then we've got, remember, the entries come in backwards order. So page number 2 starts with BBBB. Page number 3 starts with FFFF. Page number 4 starts with MMMM, and so forth. So the goal is to find the correct next page to read by comparing the target key against the data in the internal entry. Okay, so your goal is to find the maximum key that's less than or equal to your target key. Okay, so if get was provided the target key of NNNN, then the goal is to identify the offset 60, whereas page number 4, data is 4Ms as the proper entry, and repeat the search on page 4 next. One could binary search this, but the offsets are maintained in order, so I found a linear scan easiest. Right. So it's basically like scan until you hit one that's greater than your key, and then the previous entry is the one. Or if you reach the end, you're like, okay, it's the last page. Okay, so specifically for internal pages, iterate over the entries with a sliding window size too. Right. Okay. So we could use slice windows potentially. I don't know if they have added the Windows like thing to iterators yet. Last I recall it was a nightly feature, so we might not have that. But again, we're going to be iterating over entries. We could make our own iterator again for going over internal pages. So specifically in that order. One, yeah. So this is your searcher to find a left right where left is less than data, or left is less than the target key and right is greater than the target key. And skip the comparison on null. So if your target key is less than the first internal entry's data value, then your target key is not found in the B tree. Right. So we can say that lets you bail early too. So if your key is not in the is smaller than the first entry in the first page, you know it's not in the database. Okay. Once you're on a leaf page, there will be key data entries instead. Recall that there will always be an even number of offsets and entries on the leaf page, with the first entry being a key. So we can do something where we take the first entry and then we skip 2, and that's part of our iterator. So iterate over all the entries in pairs, right? Or we can do like chunks too, right? To get multiple entries at once. Okay, so let's start by implementing something that is a get. Right, okay. So let's make pub function gut. Yeah, that's how I'm feeling about it. Okay, self. So we want to have the key be a reference to, a byte slice. Again, we don't care, the slice has the length in it. We don't need to care about these other things. At least not right now. So this is a void star of data and the size, the length of it, but the slice encodes all of that. And what we want is an option of a slice, right? So yeah, if it doesn't exist, we won't get a result. We'll get none. Okay, so let's talk about the algorithm. So we start from the root page. Let's look at walk, because we'll want a similar thing here. Maybe we'll go ahead and make a struct called find. Or because we'll need stuff like move to next page, the current page. Let's start from I'm going to do it naively and say, let's just collect the pages, because we're going to need to let's just return none here. We'll probably have a early bail at some point that returns none, but now we have all of the pages. And what I want to look at is what we did in walk to say like move to leaf, because what we want to do, we want to start, if we have a metadata page, we want to go to the root page. The metadata page is supposed to be first regardless, but I don't know that there's a guarantee about that. So honestly, maybe what we could do, and I haven't thought about, should there be a get a single page method on this, which would be interesting. It'd be similar, it'd be sort of like raw pages, but without having the iterator aspect. Let's do something like this. Let's do pages, find, iter, find map is what we want. Okay, and if this is a page, we want to go if let page header metadata, and there's all that goop, and we only care about the root. Yep. Header. Then we're going to return some root, else none. Okay, so that gives us the root page. And that's where we can start our algorithm. There's a question here about, if there's no root page, we should just return. Like, I don't think there's any case where we'd have a usable database that has no root page in it. But that's a nice affordance there, that if we can't find a root page, we should just return none, because there's nothing in this database. Okay, and then we have a thing where we need, maybe let's not call it root, because we want to call current page, and let's make it mute. Because what we'll want to do is use this as a counting of where we are. And what page to move to next. Yeah, I'm thinking let's just kind of do this brute force first, and then we'll figure out ways to do it more efficiently and more cleanly. This isn't too bad. This is just, find me the page that has the metadata and get the root out of it. So now we can go Now what we want to do is look at the current page. And maybe we'll just do it with a loop for now that we'll break out of. At some point we'll do return sum, and then this is the value that we found, if we find it. Otherwise, we want to do two things. So if we're let's do here we are in the page, current page thing. We're going to do pages, current page here. I don't know if you can hear that. My cat's having a real one out in the hallway with the door closed. Okay, so we've got, we have this collection of pages. I actually wish we didn't do this and we had a method that would slice and construct the page from that slice. Maybe we'll do that later. Let's put a to-do here. Make a method that returns a page from an index into the DB. That should probably be a private method. Then we don't have to do this collect, and we can construct the page directly from a slice of the buffer. That will also potentially make it better when we are not reading the entire contents of the database into RAM, but using, you know, combination of like a page cache and seeking the file to read particular bytes. Okay, so we get the current page, and then I think we might have something on there. So we have is internal and is leaf, right? Okay, so we can go if page is internal, we'll do one thing. If it's a leaf, we'll do another thing. So if it's internal, we want to do this part of the algorithm. So we'll do let's look at the iterator docs, because there's probably this is the one thing that's weird. There's no windows on iterator, but there is on slice. We can make a peekable iterator. Yeah, let's do peekable. So the reason I'm thinking of using peekable is that we could iterate through each of the entries and peek at what the next one is. Map windows, yep. Nightly experimental fun. So actually, we could do we could do something like this. So let previous is none, and we'll say uh, for entry in page dot entries. Right, that's just to say that this is what so page dot entries, remember, returns an entry iterator, and that entry iterator returns entry of ticket. Okay, so we've got an entry here. An entry can either be key data or internal. It should be internal, right? We want the page number, and we want the data, because the data tells us the key that is the lower bound of that page. And here, I'm just going to put unreachable. We should not be getting key data in an internal page. Okay, so if we've got an entry, an internal entry, what we want to find is the actually we don't care about page no right here. Right, we're just trying to find the one that's the above the current key that we're trying to compare. What I'm not sure about is partial comp. If slices of U8s or if slices of T. Oof. Let's just try it. So we can say if key is greater than data, then what we want to do is previous is sum of entry, and we want to continue. We don't maybe necessarily have to explicitly say continue. Else we want to break out of this loop. And we might need to put labels on these loops, but maybe what we could do is make something that's a little bit more contained, where we only do this. We like call a function that does this iteration. I don't know. Okay, so if the page is internal, we're tracking what this is. Now, if we break out of this loop, then we know we either found the page that that key should be in, um, or it doesn't exist in the database at all, right? So um, so if it's before the first key in the first page, then this will be none. Um, Otherwise, what we need to do is continue this loop, like set current page. Um, this could be actually, we maybe don't need the entire entry. Maybe we just need the page now. So this is page now is U32. Yeah, so let's make it U32 instead. Um, and then we'll pull out the page number here, or maybe we do U size, right? And then this can be used to find the page in here. So we'll do a page no as U size. Right. So we can just say if it is none, um, when we do, yeah, this logic is getting kind of messy, but if it's none, then we return none. Otherwise, we set current page. Maybe we'll match instead. Match prev. Oops. Fill match arms. That's what I wanted. And this is current page is page no. And this is return none. Yeah, you need to put braces around that. The other thing that we could do here, this is actually we could say current page is prev question mark. Okay, so what are we complaining about? Any code following this expression is unreachable. Fun times. Let's get a more detailed one, because that is really vexing. I can't read it. Oh, why is it? Yeah. Unreachable macro. Why are we doing that? Okay. So, unreachable expression. That's just a warning. That's wrong because we're not done with our algorithm. Okay. Okay, so if it's an internal page, we're tracking what the previous entry was, internal entry, or the previous page number that indicates what the current page is. So if we are so we're iterating over the entries in that internal page. They should all be entry internal, right? And what we want is the page number for the page and the first key, or the minimum bound of that page. Probably not going to be actually the first key, but might be something less than that first key. And then I really wonder if that's not possible to compare. The answer is if it's greater than or equal to, not greater than. If it's greater than or equal to that, then we mark that as the next candidate page. And that'll continue until we reach the end. And if it's greater than all of the first lower bounds, then it's in that last page or not existent at all, right? Okay. You can convert a U size to a U32 in Panic if the... Oh, the problem is here as U size. Okay. Because root is a U32 in that struct. That's how it was pulled out. Okay, so we need this to be mutable. We're fixing bugs. All right. It's probably complaining about this. Yeah. Okay. So now, so we've set the next page to look at to be whatever this is. If it's again an internal page, we'll go into this and we'll scan through the internal nodes. Now, if it's a leaf page, which is the other option here, because we have already identified the metadata page, right? If it's a leaf page, then we need to do the other algorithm that they talked about. So here we're going to get pair of entries. Chunks 2. And then let's match, maybe let's say this is pair rather than destructuring it. We're going to match pair, or we could do if let. Okay. So this is going to be the pair. So we want to match on, are those... So if we're in a leaf page, a candidate leaf page, we want to loop through all of the chunks of 2, so pairs of 2 entries. And we say if key equals key data, then we just return some value data. And then at the end of this, we know we hit a leaf page that was a candidate, so we break. Again, we will clean this up to be a lot better. Okay, so is it not chunks? It is chunks. Or is that on slice? I think that's on slice. We could do a rate. That's nightly. Oh, why do you make this so hard? Yeah. Scan? No. Map windows. No, that's nightly. I seriously wonder what their concern is on having chunks or something similar to it on iterator directly. Hmm. Iter has chunks functions too, if that's what you're looking for. Well, yeah, we can just like add iter tools and move on with our lives. I'm sure there's some like internal drama in the Rust project about why don't we have chunks on iterators? Come on, people. Um, yeah. So let's get iter tools and just be happy. So now I need to look at the docs for iter tools. Docs.rs. Not Bevy, although that would be fun. Iter tools. Yeah. Okay, so we need to add this trait. And then so iter tools has chunks. Interestingly, it probably doesn't return a tuple because there's no const generic on that. Okay, into chunks is only iterable by reference. Yeah. Tuple chunks. Ooh. Really? Tuple windows even. Gosh, maybe we should use that for our other algorithm. That's tuple combinations. Okay, that's not what I want. Tuple windows, I'm not interested in. Yeah, let's just do chunks. And I'm guessing it returns or it iterates a slice into chunks. What's the item type? The item is chunk. That implements iterator. Boo. Oh, just tuples? Okay. Let's look at tuples. Tuples. There we go. Specific size up to 12. So we have to use a type hint. Okay. So first of all, let's start with what is that garbage? Okay. We need that so that we get that in our scope. And then I'm going to do tuples and give it a turbofish of that. Okay, what's wrong here? Cannot return value locally referencing local variable pages, returns value referencing data owned by the current function. we need to do this. We need to do this. Something like that. Okay. All right, let's look at a specific size, alt method, next tuple. Okay. So we have an issue of the fact that we're collecting the pages up here and we're borrowing it here, and then we're going to drop it at the end. And so the compiler thinks that this value data is not, it's going to be dropped at the end of the function. Again, this is messy code. We'll clean it up later. So what I'm wondering, actually, I think I know the answer to this. Well, let's go ahead and make that function we talked about earlier that fetches the whole page, or fetches an arbitrary page by index, right? So it'll be sort of like this, but it'll be, you know, we'll have we'll make a new page after slicing the buffer. So let's make a fun page, and self index is usize, and we're going to have it return option of page, right? So what we want to do is get the start offset of that is going to be index times 4096, right? There's a question in my mind about whether we need to end offset is start offset plus 4096. So for page 0, we'll get 0, and the upper bound, like exclusive upper bound, will be 4096. Honestly, I should extract that out into a page size constant. So what we can do is go if start offset. Actually, we just need to check the end offset, because is less than or equal to self.buffer.len. Then what we'll do is we will do page new And this will be self.buffer. We need to borrow it. And we'll do start, offset, and offset. Some else none. Okay. I feel like we should write a test for this. But let's just try it up here. Because now then we don't have to collect this. Right? We can remove this. We can say this is an iterator. We can just use the pages method. We don't need to turn it into an iterator because it is an iterator. That'll give us the start page, right? And here we're getting an owned page. So self.page, current page. And we can put a question mark on that. Because if we can't find a page with that number, then we just bail. There's nothing to look for, right? And that is still local variable page. Should we do .cloned here? The problem is that it's still, yeah. I wonder if I'm trying to the thing is this should have the same lifetime as self. And I don't think that this is going to help anything, but what if it's that? What I would rather not do is return a vec of U8. There's no reason for us to clone here. If y'all have any thoughts, throw them in the chat. Otherwise, we need to wrap up real soon. Is the issue that this is being borrowed? This borrow is still active while we're trying to return this data? Do we need to assign it? Do we need to assign it some variable that's outside the loop? Maybe even out here. I say like let mute result is none. And then down here we're just returning result. I don't know that that's going to help. Result and break. No, it's still complete. I would say that it should be possible. The data should have a lifetime of self. Yeah, I agree with you. I think the issue is that there's the page in the way. and it's saying this data is borrowed from page, but there's like a transitive borrow, like that it's not actually borrowed from page, it's borrowed from the database. Right, because page, the contents of page is a slice, right, that's borrowed from the database where it came from. And it's just, yeah, it's just a reference into that. So we've got a subslice of a subslice of a subslice going on here, and that's the thing we want to return. So how do we convince the compiler that this entry containing this slice of value data is just a reference to the buffer, just a subslice of the buffer? So here, I'm going to undo that change we just made. Because we that doesn't solve our problem. Now, the thing is, though, cloning a slice is basically cloning a pointer, right? If I do, could I do cloned here? No, it hates that. It really hates that. I shouldn't need this into iterator, right? Yeah, that doesn't make any difference. Gotta do cloned here. Okay. It yields entry tick, right? I'm there was some commentary about borrowing an iterator to make it. Yeah. Okay. Now, what we could do, um, rather than relying on going through the iterator and the borrow from the iterator, keep track of the index, right? Can your test with return directly after creation of a page? I don't understand your question, Isaac. Can your test with return directly after creation of a page? Okay, so what I'm thinking is that we do something like, rather than this, we get an offset. So tuples, and we do the same iterator, right? And then we do find map, right? And this is going to take want an enumerate in here somewhere. Um, is there something similar to like index of? I kind of want find because I want to inspect each one. As position. Yeah. Okay, so this returns some index. This is what we want. Okay, so we want position. And this will be key value here. And then we'll do if, maybe we'll just do pair again, like we did below. Okay, and then we get this if let. And we don't care about the value data. This actually maybe means that we can do something completely different in here. We don't need tuples. We can do step by. Step -1. Yeah. Let's do step by 2. And then this is just key. If let key. Okay, we can do return key equals key data. I'll just say key equals key data, else false. Right, so this is a predicate. So offset, error says that page is a local. Right, so the issue is that we're borrowing value data from page technically, and it's saying this variable doesn't live long enough to return this borrowed value. But what we can do potentially is find the position we want to get and then get the key out of there directly. I don't know. It's worth a try. We're running over my intended length. I think a few more minutes is fine to try to wrap this up. We know the keys are in pairs, so key value. We'll iterate over the entries in 2, and then if we find the key, so if we don't find the key and we're in a leaf page, we should just return none, right? So again, there we can use the question mark. That's pretty nice. Let me comment this bit out. Okay. So now we know that offset is a usize into the page's entries. So we can say page dot get entry, and here's where we need, so the value, this is the position in this iterator that skips. So what we want is offset times 2 plus 1. And I'll call this value data for consistency again. If let and I'm guessing that what will happen here is we'll get the same error. Let's get rid of this. It doesn't. So now it's like you can't. Partial equal can't be used on this. But key is a. Oh, I shadowed this. We'll only call it entry. I didn't mean to shadow that in there. Okay. Yeah, I've been doing too much TypeScript. You can tell. Do TypeScript in my day job. Okay, and that needs to be renamed. Okay, so we had another. I feel like is another variant of the overlapping borrows, but is two immutable borrows. So I don't think that we'll get to clean this up this time, but and we don't need these generics now. Okay, now it's just complaining about it's never used. So let's do a little bit less than 10 more minutes. Let's look at their task. So, they've got the goop about the DBT thing. Interesting. So this is a test thing. So we can do something like this, right? What does their test get function do? All right, well let's make a function similar to that in our main, and then test get, and this is gonna take a DB, and then let's say key is a stir, and it's not going to return anything. It's just going to print whatever it, like this sort of stuff, right? Okay, so we're going to say let bytes is stir dot or key as bytes. Does that not give us a U8 slice? It does. Okay. Okay, so our thing is either going to panic if it doesn't find it, or it's going to return none, right? We could have it do something like result option or option result or something like that. Probably result option, but we're not doing that. So let's do match db.get bytes. Right? Okay, if we get some value, then we're going to do similar to what we did, say let value standard stir from UTF-8 value. Yeah, I'm just gonna unwrap that. We'll let it blow up. So we'll print line, and what do? They say key and we'll say key data is value stir. Yep. Otherwise, if it's none, then we print line key not found. Right, and they're, in C style, they're using integer return values to indicate that this is successful or not. Okay, and then their main, they do test get, and they use these different keys. Okay, so we're going to do the same. And they are not doing stat print in here, so we'll comment that out for now. Okay, so let's do test get, and we'll pass db, and the key we want to pass is this. And we'll do the same for this fake key. And let's learn all the ways that our algorithm is broken. And then we'll end the stream. Wow, that's a long key. Yikes. My editor can't even scroll all the way over. Can you here? Oh, that's what's wrong. Like, I didn't have the editor fully maximized in the window. Too many parens. Okay. Let's just do that. All right. Run. Okay, I fully expect something to completely break because I did it wrong. Or go in an infinite loop because I didn't check the conditions. Yeah, I'm pretty sure that's in an infinite loop. All right, so I think what we'll do next time is we'll debug why that's an infinite loop. We'll probably find some ways to simplify our algorithm there, and then we will see if there's anything else to move on to. All right, thanks everybody for coming, and I'll see you next time.